Hello everybody, welcome back. We're gonna try it, but I think after cutting it down to just essentials, I'm not going to talk about applications too much. I do want to talk about the geometry of what's going on and how and why these things work the way they do. But I'm going to focus on purely mathematical aspects of this, and so I'm pretty sure we can trim those last 3 sections of material down to just this one video, and then I'll give you this one more homework assignment. So you will have a written homework, and I'll try to keep that pretty terse, nothing too fancy on it, and that will be due Friday. So you have 4 days. Try to get it done by Thursday so that if you do get stuck on something, you can email me and have enough time for me to get back to you. So just remember that. Okay, so let's get started, and the first thing I want to talk about is orthogonal projection. And at first I just want to talk about it as, let's say, of one vector to another. And maybe we want to say another's line, if you wanted to be a little bit careful. So anyway, the problem here, so what's happening is I have 2 vectors. Let's say this one's, let's call it V. Let's call this one U, like we normally do. What we want to do, the first problem we want to be able to answer is, we imagine just the entire line that U sits on. And we want to take the projection, shortest distance at a right angle like this, of this vector down onto U, and we want to know what this vector is. So if I take sort of the point on that line that my U vector sits on that's closest to this V point, and then I take that vector that takes me there, how do I find that thing? And then once I'm able to find that, we'll also be able to find this piece up here. So let's create names for these. So this vector right here, I'm going to call the projection onto U of V, where I really mean onto U's line, that entire line spanned by U. If my U vector was over here and say my V vector was over here, then my projection would be a vector over here that wouldn't even overlap with U at all, but it would be on the same line. So there's a little bit of a distinction there that's worth remembering, but I like this notation, so we'll just stick with it. So I'm going to say the projection of V onto U, and then this thing right here will be known as, let's say, the component of V orthogonal to U. And one thing we can know right away is, if I know this projection vector, then what's this vertical one here going to be? Well, if you look at this projection vector, and I was to move it, I accidentally didn't drag the whole thing, and I moved it up here, a copy of it, then if we just reversed its direction, so I took minus that projection, what we end up getting is that if I travel V and then minus that projection, that vector here that I'm getting is exactly this vertical one over here. So that means that this thing is going to be equal to V minus that projection onto U of V. So let's clean this picture back up. There we go. So we start with this U here and this V here, and then we want that projection of V onto U, and then also if I take V minus its projection onto U, we'll get this component here that takes me from whatever the nearest point along U's line is to V, straight to V in a way that's orthogonal, perpendicular to U. And being able to do those two things is going to be very powerful for us. So let's figure out how we do that. So first off, imagine if I have my U and my V let's figure out what the formulas ought to be for this. First, imagine we just move this so that my u is sitting like on an x-axis here, and then my v is just coming up, kind of like how I did the first picture. And the first thing we'll notice is if I imagine sort of this point here is my origin, and look at this like a unit circle. This is supposed to be a circle, so bear with me on that. Let's say the angle between them, let's call that theta. Whatever the length of v here is, so my magnitude of v, this would just be the x-coordinate. So in other words, the length or the magnitude of that projection onto u of v. Well, what is that? That's just magnitude of v, because that's what we've stretched the radius of the circle to. It's not a unit circle, it's a magnitude of v circle. So it's going to be the magnitude of v times the cosine of that angle between them. But wait, recall that u dot v, the dot product, one way to think about that, at least in 2 and 3 dimensions, was that was the magnitude of u times the magnitude of v times the cosine of the angle between them. So the only thing I'm missing is that magnitude of u here. So what do we have so far? We have that the length of the projection of my v vector onto my u vector is equal to u dot v, except we need to divide off that length of u. So then what can I do? Well, now I can get a formula for this projection really easily, because, well, if I know the length of that projection vector, so here's u, if I did that projection, if I know what length I need, then all I need to do is take that length and scale. I need a vector in u's direction. In particular, I need a unit vector in u's projection. So I take u and normalize it. If I take u and then scale it down by its own length, now I've got a vector of length 1 unit length in the right direction, and then I just scale it, multiply it by that length of that projection that I need, and that would get me there. So now I can get our formula. That projection is going to be this length, the length I wanted the projection, which we already found was u dot v divided by magnitude of u. And then I'm just going to use that to scale a unit vector in u's direction, which would be u scaled down by its own length. But of course, this gives me a little bit nicer formula because, okay, I've got u dot v, whatever number that is, and then I've got magnitude of u squared that I'm scaling u with now, not the normalized u. I just took this number, moved it in there, and wrote it as squared. And now the one bit that we can do, a vector dot itself is its magnitude squared, in case you forgot that. So that gives me my formula. And this one here is supposed to be the v. So let's save that. It's a very important formula. So let's say thus the projection onto u of v is that. I take u dot v divided by u dot u, and then I use that number to scale u. Okay, and then, and the component of v orthogonal to u Well, now we have a nice formula for that, because remember, we figured out that that would just be v minus this projection. So I could just take v and then subtract off its projection onto u. So if I had my vector v, I had my vector u. If I look at its projection onto u, if I subtract that off, that would give me this vector here, which is exactly that component orthogonal to u. That gets me to v. All right. Now, once we can do that, there's all kinds of geometric tricks and things that this helps with. But before we move on to that, I want to talk about what do we mean when we talk about a set of vectors being orthogonal. So this is a set of vectors is called orthogonal. If each pair of vectors in it are orthogonal. So let's write that in a little bit of notation. So if I have a set of vectors, let's call them u1, u2, up to some un, then we call it an orthogonal set of vectors if each pair, if I take a u, let's say ui dot uj equals 0, when those are actually two different things in the set, of course. Something dot itself is just its length squared, but if my things are perpendicular to each other, the dot product should be 0. We saw that before. Okay, so why would an orthogonal set matter to me? That's a good question. So particularly this is helpful when we're talking about subspaces and working in subspaces. So a basis, which you remember what that means, a basis for a linear subspace. So we have some basis for some subspace is called my handwriting is getting wild. An orthogonal basis. If it is also an orthogonal set. And there's also easy ways you could check if a set of vectors is orthogonal. So in particular, note a set of vectors, let's say u1, u2, up to some un. These are supposed to be vectors. Is orthogonal, meaning it's an orthogonal set, if let's say when we let u, let's just say this is the matrix that has those as its columns. So if I look at them as the columns of a matrix, then all I really do is just say, well, U transpose U should be a diagonal matrix. And this is actually really easy to see. If U's columns, its columns, are an orthogonal set, and then I transpose U, so here's my U transpose, and I perform that multiplication, this row to this column that's just that vector dot product itself. And so in that entry is going to be its length. But this first row to this column, that's two different guys, and they're supposed to be orthogonal. So, okay, this would be that thing's length. That would be 0. Dot product of orthogonal things is 0. So all the other entries would be 0. But then when I take the second row, second column, that dot product itself, well, that would just be its length squared. And then, okay, my second row dot product of first column, well, those are two different of the vectors, so that would just be 0. Everything else would be 0. And of course, this pattern would continue, and you end up with this diagonal matrix. And so that's one quick way you could check using a calculator to do all those dot products for you. Every pair of dot products, you can check them all at once by just doing this big matrix multiplication. Another piece of language here. An orthogonal set of vectors is moreover called orthonormal. So here's another piece. Orthonormal if each of the vectors in the set have length 1. And before we had a word for that, we called that being a unit vector. So, and then a basis, which is an orthonormal set, is called, and this is, I probably didn't even need to write this, an orthonormal basis. I hate this terminology because it's hard to say these words, but it's very standard, and so I wanted to go over that real quick. So anyway, on our way to learning how to find such things, first let's say, how do I check if a set's orthonormal? Note, use columns. So same trick as for the orthogonal. Are orthonormal if I do U transpose U and I get an identity matrix. So why would that be? Well, here's my U transpose, so its columns are going sideways. Here's my U, its columns going vertical. Along the diagonal, I'm taking one of those vectors dot product itself, and if its length's 1, a vector dot product itself is its length, its magnitude squared. Well, 1 squared is 1. So my second row, second column would give me a 1. My third row, third column, I get a 1. So I get those 1s all down the diagonals, and every pair of vectors in this set was supposed to be orthogonal, so when I dot product two different ones together, I should get zeros. So that's where that's coming from. And so you can check, is this really an orthonormal set? I can check it really easily that way. Now I want to talk about one of many things, but let's ask the question, what's nice about an orthogonal basis or an orthogonal set? So one thing about what's nice about an orthogonal basis, so one thing, so let's suppose I have some subspace. So say we're in 3-dimensional space. So I've got this, this 2-dimensional plane here. And then I've got some vector, let's say here's the origin, and I've got some vector shooting up off that plane. So let's say like here's my y-axis, well, it's not really y-axis. We want the plane to be able to be tilted, so let's not call those axes. Let's just say I've got some plane. It could be tilted somewhere, but it does run through the origin, and I have some vector off the origin. So let's say, here's my vector v. Now, suppose I knew a basis for this plane. So say I had a basis, u1, u2. Now, if I wanted the projection onto this subspace, so let's call this a subspace W, which is going to be the span of those two U's. Oop. Okay, so I have this subspace, it had those two basis vectors, and I want to look at this guy that's not in that subspace, it's shooting up off of it. I want to look at its projection onto this subspace. How would I do that? Well, if those basis vectors are actually orthogonal, this is a right angle between them, then this actually works just like it does in our usual coordinates, where say I have an x-axis, a y-axis, we know it's a right angle between them. If I have something up and I want to look at its projection down onto the x and y plane, you're just killing off the z coordinate. And so you would just look at this guy's y coordinate and this guy's x coordinate, and that would be it. That would lead you straight to that projection point. And that works as long as these things are orthogonal. If they're not, you run into some trouble. So let's see what that means. So if I want to project, so let's write this as a, maybe I'll write this as a theorem really quick, and then I can doodle some more pictures. So let's say theorem, if we have some orthogonal basis, so let's say u1, u2, up to some n-dimensional subspace here, is a basis for the subspace, let's give it a name, let's call it W, then I actually can talk about the projection of a vector onto a subspace, just like I was doodling there. And if I have an orthogonal basis, is a basis, oops, I goofed, is an orthogonal basis for the subspace, then I actually get a nice formula. The projection onto that subspace of some vector, let's call it V again, is going to be project V onto each of those basis vectors and add them up. Because so you're just doing it component-wise, coordinate-wise. All the way to the end. And we have a nice formula for that. What is this? This is just v dot u1 over u1 dot u1 scale u1 plus v dot u2 over u2 dot u2, and then use that to scale u2 and keep going, right? So we have this nice sort of relatively straightforward computation using these dot products, which are really basic, simple algebraic operations, to be able to do this fairly sophisticated geometric thing of having some subspace, and it doesn't have to be a two-dimensional one we can actually visualize, and then having some vector that shoots up off of it, being able to project that vector 90-degree projection and find its projection onto that subspace. And not only that, once I know its projection, I can do the same subtraction trick and get that orthogonal component. In other words, I can get a vector that is orthogonal to that subspace. In other words, it's orthogonal to every vector in that subspace's basis, or any vector in that subspace, and it's exactly what I would need to add into its orthogonal basis to still have an orthogonal basis, but now generate anything that I could generate with this subspace plus this new vector. So I can extend the basis and keep it orthogonal. And that's a really important idea. So let's make a note, and the component of the orthogonal to the subspace W is, now remember what we did, we took V and then minus its projection onto that subspace. But what just happened here? Its projection is this big sum of these things. In other words, I take V minus its projection onto each of those vectors from the orthogonal basis. And of course I'm distributing the negatives, so I would just go through and subtract all these off. Minus onto the end, and so I could clean that up. That's going to end up looking like V minus V dot that first vector from the orthogonal basis over it dot itself, scaling it, minus V's projection onto U2, which would be V dot U2 over U2 dot U2, and then using that to scale U2, minus V dot U3 over U3 dot U3, and using that to scale U3, minus, and so on until you're done. Now, this gives us something quite nice. It gives us a way to, given any basis for a subspace, if I want an orthogonal basis, how can I get it? And this can be very useful, especially in computer algorithms and things like that. Being able to take some subspace and replace whatever basis you can just find for it algorithmically with one of these bases where all the vectors are orthogonal to each other. And not only that, you could also scale each vector by dividing them by their own magnitudes to be all unit vectors, and then get an orthonormal basis. And for many algorithms, this turns out to be very, very useful. And so in case you run into those applications, I want you to be comfortable with the process that's going on when you pull that move. And so this is what's called the Gram-Schmidt. The Gram-Schmidt process. So this is section 6.4. Okay. Now what can we do? So here's the problem. Given, let me try to be a little more careful with my handwriting. Given a basis and now let's say we're given some basis. Let's call it U1, U2 up to UN. For a subspace. How can we find an orthogonal, or even if you want to take it that one extra step, an orthonormal, which means you just find the orthogonal basis and scale them to have length 1 basis for the same subspace. That's the problem we want to solve. So let's try to figure this out. So I have some subspace that I'm starting with, and here's its basis. And I want to get a new basis where they're all orthogonal. And now what we do is we go one step at a time. So one step at a time. First, we didn't say we care exactly which directions all these vectors are pointing in. We just care that they're all perpendicular to each other. So first thing I could do is just let my first new vector be the first old vector. Don't do anything with it. Right? Then, what can I do? Well, I've got this now this is my v1. It's the first vector of my new basis. Now, I look at the next vector in the old basis, and now what do I want? I don't want to add it. It's not orthogonal. So what do? And the idea is, well, instead of adding it, let's add its component orthogonal to what I got so far. See, now there's still a linear combination, some scalar multiple of this guy plus this new component that then gets me there. And so these two vectors, this orthogonal component, whatever it is, it wouldn't be u to itself. I'd have to do that subtraction. That vector plus that previous one generating that line is still going to span the exact same subspace as the original first two vectors spanned. So what am I saying here? I'm saying let our new second vector be the old second vector minus, how did we get this orthogonal component here? We subtracted the projection, right? So what do? We subtract its projection onto my first guy. In other words, we take u2 and we subtract off u2 dot v1 over v1 dot v1, scaling v1. I subtract off its projection onto v1. Then I just keep going, right? Then, how do I find my v3? Well, now I've got this subspace spanned by v1 and v2 that I've made by doing these orthogonal components. Now I have some new vector, right? Or well, let's say here's the origin. Now I've got some new vector that shoots up off this subspace. Okay, well now I just want the component of it orthogonal to that subspace being generated by my new vectors I've already got. And then I replace that vector in the basis with that orthogonal component instead. And so, okay, what's that going to look like notationally? Well, I'm going to take v3 is going to be my old third basis vector minus its projection onto, let's say, v2, also minus its projection onto v1. Because that would be that component orthogonal to that subspace generated by those first two vectors. And of course, algebraically, that's u3 minus u3 dot v2 over v2 dot v2 scaling v2 minus u3 dot v1 over v1 dot v1 scaling v1. And of course, these are all vectors. And we keep going. and keep going until all of the original basis vectors are replaced by what I here was calling my v's, right? So keep going till you replace your un with a vn following this process. So after this process, that new list of what I was calling the v vectors is an orthogonal basis for the same subspace. And if I want to go further, I could take each of those and then scale it by 1 over its own magnitude. So take all those, divide each of them by its own magnitude. And then I would get an orthonormal basis for the same subspace. Orthonormal bases are particularly nice. For instance, imagine just like our xy plane, right? You're used to this orthonormal basis where you have my unit vector 1, 0 and my unit vector 0, 1. But I could just as easily have had, let's say, a unit vector 45 degrees northeast, which would be square root of 2 over 2, square root of 2 over 2, and then something perpendicular to that. So let's see, what would this be? Negative square root of 2 over 2, square root of 2 over 2. Those are both length 1 because those are points on a unit circle, and they're orthogonal. So this is an orthonormal basis for the plane. Matter of fact, if I took any point on the unit circle and then any other one that's 90 degrees from it, then those two vectors would be an orthonormal basis for the R2. So an orthonormal basis is not at all a unique thing, but being able to find one is very useful. This is related to a lot of things in computer algorithms in particular, but it also makes it much easier to deal with these geometric things like projections onto the subspaces. And those are also really interesting tricks because, for instance, maybe if you've done Cal 3, we often use Lagrange multipliers to answer a question like, what point on the plane here is nearest to this point that's not on that plane? And okay, what's a new way I could answer that then? We'll find any point on that plane and subtract it to shift this whole thing to the origin, and then shift this point along with it. So now I got a plane that passes through the origin, meaning it's a subspace now. And I can think of that point here as a vector. And then I can just find two vectors that aren't parallel that'll sit on that plane, which is usually pretty easy. Just plug in a couple different numbers and solve for whatever other numbers for the other variables. Now replace those, modify that into an orthogonal basis, and then I could just look at the projection of that point, thinking of it as a vector now. I could think of that projection onto this plane. And then, after I'm done with all that, shift everything back by adding that point that I did to move the plane to where it touched the origin, add it back onto everything. And now I've done a purely, relatively quick algebraic way of solving that problem, and I didn't have to do these partial derivatives and Lagrange multipliers or any of those other methods that you would learn in like a Cal 3 class. I can do it purely geometrically, just using linear algebra, instead of having to go through all that analysis. So there's ways you can do pretty sophisticated geometry and avoid the calculus. There's lots of computer algorithm stuff that applies these sort of techniques. So I just wanted to make sure we understand the geometry of how that works really, really well. One more thing, I want to do an example, and then we'll call it quits. So let's say example. So in the textbook, one of the examples that it asks us to find an orthogonal basis for the column space of a matrix. And I'm just going to write down one of the examples. So this one, it gives me 3, 1, 1, or no, negative 1, 3, negative 5, 1, 5, negative 7, and then it gives me a third column, 1, 1, negative 2, 8. So it gives me these 3 column vectors. And now remember, the column space is just the subspace they generate. So what am I going to do? I'm going to say, okay, well, let my first vector in my new basis just be the first vector of the old basis. Then I would let my second new vector, I want that component of it, of my old second vector that's orthogonal to the subspace spanned by the first one, that's orthogonal to the line. So I would take my old second vector and then subtract off its projection onto the previous stuff, which is going to be, okay, I take my u2, which is the negative 5, 1, 5, negative 7, negative 5, 1, 5, negative 7, minus, now I want to do this projection here, and you haven't seen me write one of these things yet. I tend to fill a lot of space when I write these things. So projection of u2 onto v1, so that's going to be u2 dot v1. My u2 is this thing here again. So I'm going to have it dot my v1, which was 3, 1, negative 1, 3, divided by my v1 dot v1, 3, 1, negative 1, 3, dot 3, 1, negative 1, 3. That's supposed to be a negative 1 here. And then I'm using that to scale v1. So v1 is 3, 1, negative 1, 3. Now that gives me a lot of work to do. So let's figure out what all these numbers are. So I have negative 5, 1, 5, negative 7. And then minus, let's figure out what these numbers are. So what's my dot product here? Negative 5 times 3 is negative 15. Plus 1 times 1 is 1. Plus 5 times negative 1 is negative 5. Plus negative 7 times 3 would be negative 21. So what do I've got? I've got negative 15, negative 21, so that would be minus 36. Then minus another 5, so I've got minus 41, and then plus 1, so minus 40. And then on the bottom here, I've got 9 plus 1 makes 10, plus negative 1 times negative 1 is 1, so we've got 11 plus 9, so that's 20. And then I'm using that to scale 3, 1, minus 1, 3. And so let's clean this up again. So I've got my negative 5, 1, 5, negative 7 vector. Minus, except this negative is going to make that a plus. 40 over 20 is just 2 times this vector. And so, okay, so I've got negative 5 plus 2 times 3 would be negative 5 plus 6. So I'm getting 1. Then I've got 1 plus 2 times 1 would be 1 plus 2 is 3. 5 plus 2 times negative 1 would be 5 minus 2, that's 3. And then I've got negative 7 plus 2 times 3 is 6, so negative 7 plus 6, that's going to be negative 1. So there we go. So let's recap what we had. As my v1, we just reused the first of the old vectors. Let me drag that down here for us. Sorry, it's moving slow. Right? And now we've got our v2. You found that one too. So now we just got to get a v3. So now, finally, we had 3 vectors in that basis, so we got to keep going. Finally, v3 is going to equal u3 minus the projection onto each of these previous things. So onto v1 of u3 minus the projection onto v2 of u3. And so we're going to have u3 minus u3 dot v1 over v1 dot v1 minus u3 dot v2 over v2 dot v2. I stopped writing the arrows just to make this go a little quicker. So let's fill in what all those things are. So what was our u3? Let's copy that real quick. So our third vector here was this guy. Okay, so here's my u3, and now we want to do minus u3 dot v1, which we had written up here, 3, 1, negative 1, 3, over v1 dot v1, 3, 1, negative 1, 3, dot 3, 1, negative 1, 3. And then we're using that to scale v1, so 3, 1, negative 1, 3. And then minus, I got this, a new fraction dot products, my u3 dot my v2, which we wrote down what that was up here, 1, 3, 3, negative 1. So 1, 3, 3, negative 1 over my v2 dot v2, so 1, 3, 3, negative 1 dot 1, 3, 3, negative 1. And then we're using that to scale v2, so 1, 3, 3, negative 1. Okay. Oop. This is supposed to be an 8. That would have threw us way off. Okay, so let's figure out what all these numbers are. So, okay, I've got my 1, 1, negative 2, 8. And then minus, let's figure out this fraction here. So I've got 3 plus 1, so that's 4, plus 2, so 6, plus 8 times 3, so 6 plus 24 is 30. Now on the bottom here, we already did this once. 9 plus 1 plus 1 plus 9 is 20. And then I'm using that to scale 3, 1, negative 1, 3. And then over here, let's figure out what that fraction is. Okay, on top here I've got 1 plus 3 plus minus, sorry. So I've got 1 plus 3 minus 6 minus 8. So this would be what? 4 minus 6 would be negative 2 minus 8 would be negative 10. So I have negative 10. Over on the bottom here, that's 1 plus 9 plus 9 plus 1, so we're 20 again. And that is scaling 1, 3, 3, negative 1. Okay, so now let's clean this up. This is 3 halves and this is a half. So let's do everything in terms of halves. Maybe that'll make the fractions a little easier to deal with. So let's see, if I rewrite this one as 2 halves, negative 4 halves, and then 8 would be 16 halves. Let me fix my left bar here. Then I have minus 3 halves times each of the coordinates of the second guy, so that would become 9 halves, 3 halves, negative 3 halves, 9 halves. And then finally negative, negative, so plus 1 half times those guys, so 1 half, 3 halves, 3 halves, negative 1 half. Now let's bring that all together, and what are we going to get? So we have 2 minus 9 plus 1, so that'd be negative 7 plus 1, negative 6 halves. 2 minus 3 plus 3 is just 2 halves. Negative 4 minus negative 3 would be negative 4 plus 3, so minus 1 plus 3 is 2 halves. And then finally, 16 minus 9, so that would be 7 plus negative 1, so 6 halves. And so what are we getting? We're getting negative 3, 1, 1, 3. So we can use that as our V3, and now we've got all the vectors we needed for an orthogonal basis. So thus, what's my set of vectors here? Well, we have our V3, so my third one was negative 3, 1, 1, 3. And let's go back to the first two. My V2 was 1, 3, 3, negative 1. And my V1 is that. And that is an orthogonal basis generating the same subspace, which was the column space, that matrix. Now, if I wanted to take it a step further, so moreover, if I took my, so let's say note, my length of V1 is going to be square root of, take its coordinates squared, so that would be 3 squared plus 1 squared plus negative 1 squared plus 3 squared. That is what? That's square root of 20, which if you prefer, you could think of that as 2 root 5. And these two guys are actually going to have the same lengths. So my V1, V2, and V3 turn out to have the same lengths here, which is kind of nice. So I could actually say, if I take my V1 and then scale it by dividing each coordinate by its length, do the same thing with V2, do the same thing with V3, what would those vectors end up looking like? V1 was 3, 1, negative 1, 3. Well, now it would be 3 over 2 root 5. Negative 1, was it negative 1? Yeah, 1, sorry. 1 over 2 root 5. Negative 1 over 2 root 5. 3 over 2 root 5. And then, same thing here. Fill in that divide all its coordinates by its length, do the same thing with the other two vectors, and then you would have an orthonormal basis in case you really did need to go that extra step and get a list of vectors that you could use as a basis and be able to treat like an actual coordinate system, like nice unit coordinates. This is very useful, lots of computer algorithm applications, things like that. Mainly, I just want to make sure you guys understand the geometry of where it comes from, that idea of you're just doing these projections and subtractions, and it allows you to abstract these perpendicular pieces, and that actually lets you perform a lot of nice geometry tricks. And there's plenty of applications and things you can find in this book that we didn't have time to cover, or online, or you may run into them in your other classes. And I think we've covered enough stuff in this course that any of those applications that you end up becoming interested in or needing to learn, you ought to be able to handle it. So I think that's going to be the end of the course. And so I will say thank you. Homework due Friday. And the exam's coming. Thank y'all.